Okay, welcome to the first part of my talk for the Nearly Carbon Neutral Geometry and Topology Conference. Thank you to the organizers for having me. This talk is titled A Quantified Local to Global Principle for Anosov Representations. My name is Max Riesenberg. I'm finishing up at University of Texas at Austin this summer, and then I'll be starting a postdoc at University of Heidelberg in September. So in part one of this talk, I want to talk about a classical setting. One way to view Anosov subgroups is as a generalization of undistorted or convex co-compact subgroups of isometric groups of hyperbolic spaces. So in the first part of the talk, I'm just going to review some things about Teichmuller theory and undistorted subgroups going beyond Teichmuller space. In the second part of the talk, I'll talk about Anosov subgroups in higher rank, something about the structure of higher rank symmetric spaces, a definition of Anosov subgroups that's suitable to this setting. It's a direct generalization of the undistorted condition in higher rank that's due to kappa Levenport T. And I'll talk about some applications of a quantified local to global principle that let you prove explicit perturbation neighborhoods. They let you prove certain explicit bounds for perturbation neighborhoods of Anosov representations. Okay. So I just want to start the story with something familiar with classical Teichmuller theory. So for any closed connected oriented surface, you can define of genus at least two, you can define Teichmuller space to be sort of the space of marked hyperbolic structures on a surface. So that's the space of homeomorphisms F from this topological surface S to a surface X that's hyperbolic, by which I mean it has a Riemannian metric of constant curvature -1. And there's a natural equivalence that you put on these homeomorphisms to get what you call Teichmuller space. So one other way to interpret Teichmuller space is as the space of discrete and faithful homomorphisms from the fundamental group of the surface into PSL2R, which you can think of as the orientation preserving isometries of the hyperbolic plane. And we take these homomorphisms up to conjugation by PSL2R. So how does this correspondence between geometric structures and representations work? Well, let me just describe this in an example. So what you want to do is draw a regular octagon in the hyperbolic plane. So that's an octagon where all the side lengths and all the angles are equal. If you draw this octagon really small, then it's basically an octagon in Euclidean space, and its angle sums are too big to add up to 2 pi. And if you draw it really big, then its angle sums are too small because angles at infinity are 0. So somewhere in between, you manage to find a regular octagon whose angle sum is 2 pi. Once you do that, you can glue its sides in pairs. So for example, in this picture, I glue its sides, just opposite sides together. And you can check by an Euler characteristic calculation that this surface is surface of genus 2. So that's one way to build a geometric structure on a surface. Just get it by pasting the sides of a polygon together. Now, after you've done that, what you can do is choose a generating set of curves on the surface. So I've chosen this green, pink, blue, and yellow curves. In my fundamental domain in this octagon, they look like this. And each of these curves lifts to a direct transformation on the universal cover of S. And that universal cover identifies the hyperbolic plane. And you can see how each of these loops, how the corresponding action of that loop acts as a deck transformation on the hyperbolic plane. So for example, let's say this blue loop A, that might as well, so this blue loop A corresponds to transvection, and up to conjugation, this blue loop might as well be a diagonal matrix, lambda inverse. And the lambda, the actual distance that you translate along here, is determined by the fact that this is a regular octagon with angle sum 2 pi. So that's the calculation here. So that calculates how A acts on the hyperbolic plane. And then each of these other elements of the fundamental group should act in a similar way. You just have to conjugate by rotation. Okay, so that's one way to go from a geometric structure on a surface to a representation of the fundamental group. And that's what I've drawn here. Later in the talk, this specific representation will show up again if you make it through to the end of part 2. Okay, so what do I want to emphasize out of this picture to carry forward? So first of all, we used a geometric structure on the surface to produce a discrete representation of a group. So a discrete subgroup of the Lie group, PSL2R. Another important property of Teichmüller space is that if you deform a representation of Teichmüller space, you still get a representation of Teichmüller space. If you deform a hyperbolic structure on a surface, you still get a hyperbolic structure on the surface. So stability is a really important property that we should focus on. It's really cool that these representations correspond to geometric structures. And that's something that becomes a little bit more subtle when you look forward to Anosov subgroups in general, but still kind of works out. And there's all kinds of interesting aspects of Teichmüller theory that I won't talk about today, and but you can still ask questions about in the larger story of higher Teichmüller theory or about Anosov representations. But let me not say anything about this now. Right. So to sort of frame where this talk goes in the second half, especially, what we've talked about so far are discrete and faithful representations of the fundamental group of a surface into PSL2R. This generalizes to Anosov representations in a big way. So for Anosov representations, you can replace the fundamental group of a surface with any Gromov hyperbolic group, and you can replace PSL2R with any real semi-simple Lie group. So I've drawn this sort of, I guess, Venn diagram, where the most general concept is Anosov representations in semi-simple Lie groups. The most specific thing in this picture is closed surface subgroups in PSL2R. That's Teichmüller theory. And in between, there's an intermediate notion, and that's the focus of talk 1, undistorted subgroups in the isometry group of hyperbolic space. Before I explain why the thing I just said is can be a really good generalization of Teichmüller theory, let me just describe how maybe one way of zooming in is not so good. If you consider a closed hyperbolic manifold of dimension at least 3, you can still construct this representation of its fundamental group, the holonomial representation, and it's still a discrete representation, so that's great. But unfortunately, these representations lack interesting deformations. So in a sense, this fits into the picture, but it fits in a way that in a way that I'm going to consider boring for the purposes of this talk. So for example, something else you could think about is including the representation group including the fundamental group into PSL2R via one of these representations from Teichmüller space that we had before, and then including this into say PSL2C, and then deforming. So that's gives you a larger deformation space. Okay, and such things that you construct will be undistorted subgroups of the isometry group of hyperbolic 3 space. So that's what I consider a good generalization. So let me give you a definition. First of all, if you have a finitely generated subgroup gamma, then you can choose a finite generating set for it, and you can define the word metric. So for any element of gamma, you can express that element as a word in the generators. And the shortest such word is called the word length of that element. And if you do this carefully, you set up a word metric on the group. So that's the metric that I'm putting on the domain. And then I'll consider an orbit map. So I already have it as a subgroup of isometries, so I just let it act on some point in space, and I get an orbit. And I say that a finitely generated subgroup gamma of the isometry group of hyperbolic space is undistorted if any orbit map is a quasi-isometric embedding. So there exists a point and constants, C1, C2, C3, C4, so that for every element of gamma, we have these two inequalities. So the first inequality says that the word length of gamma is a lower bound for the distance between points in the orbit. And the second inequality says the distance between points in the orbit is a lower bound for the word length in a coarse by Lipschitz sense. Okay. And an important fact, slight rephrasing of this definition, a finitely generated subgroup of isometries of hyperbolic space is undistorted if and only if any orbit map sends geodesics to quasi-geodesics. It's a slight rephrasing of this definition. Okay. Right. So let me just go over some basic properties of undistorted subgroups of the isometries of hyperbolic space. First of all, the representations from Teichmuller space are undistorted. Okay, so this really is a generalization at all. Second of all, any undistorted subgroup is discrete. That's a general fact. And then last, undistorted subgroups of the isometry group hyperbolic space are stable. Okay, so like I said before, if you consider Pi1s, including into PSL2R, using a representation from Teichmuller space, that's an undistorted representation. Then you can include it into, you can include this hyperbolic plane into a larger hyperbolic space. You get this inclusion, and by the definition of undistorted, that's still an undistorted subgroup of this larger space, and then you can deform that. So this is a way that leads to, this is a way to construct other undistorted subgroups, for example, quasi-Fuchsian subgroups of hyperbolic tree space, for example. Okay. Okay, so an important fact here in this course study of groups is the Milnor-Schwarz lemma. It says that if a group gamma acts properly discontinuously co-compacting by isometries on a proper geodesic metric space X, then gamma is finally generated and any orbit map is a quasi-isometry. Okay, so this actually immediately proves part one. If we have a representation for Teichmuller space, we know that it corresponds to a geometric structure on a surface, on a closed surface. So the action of the fundamental group on the hyperbolic plane corresponds to the action of Pi1s on its universal cover by deck transformations. That action is properly discontinuous. It's co-compact because the surface is closed, it's compact, and the action is by isometries because of the because it's a geometric structure. Okay, so that already proves part one. Okay, next, why are undistorted subgroups discrete? So if you have an orbit that's not discrete, if you have a subgroup that's not discrete, then you can find a sequence of distinct elements gamma n that accumulate in the orbit. And in particular, they accumulate, they accumulate in the group, and they in particular accumulate in the orbit. So you have a sequence gamma np in the orbit, accumulating to some other point in the orbit that I called gamma infinity p. Okay, well, right, so then the undistorted condition says that I have a lower bound here, that each of these elements, gamma infinity inverse gamma n, has a word length, and that word length is a lower bound for the distance between p and its translate under this element. Now this action is by isometries, so this distance is equal to the distance where you use gamma infinity to move the points, and since gamma np approaches gamma infinity p, this distance goes to 0. But on the other hand, this set gamma infinity inverse times gamma n is an infinite set of distinct elements of gamma. So the word length of this set is unbounded. So this goes to infinity. So that's a contradiction. I said that infinity is a lower bound for 0. So that tells you that undistorted subgroups are always discrete. And I didn't use anything special about negative curvature here. It's just a general fact. Okay, and for the last point, that undistorted subgroups are stable, this actually does require a lot of the features of negative curvature, features of hyperbolic space. So I want to tell you about the classical local to global principle. It says that for all for all possible quality of quasi-geodesic, so for all set of constants C1, C2, C3, C4 positive, there exists a scale L so that every L local C1, C2, C3, C4 quasi-geodesic in Hn is a global C1 prime, C2 prime, C3 prime, C4 prime quasi-geodesic. It says that for every possible quality of quasi-geodesic, if that quality holds on a large enough scale L, then that sequence is a global quasi-geodesic for some other quality, slightly worse, maybe substantially worse. By L local quasi-geodesic, I mean this property holds on subsequences of length L. Okay, so let me explain why the local to global principle implies that undistorted subgroups are stable. So assume that I have an undistorted subgroup. That means there exists a point whose orbit map sends geodesics to quasi-geodesics. And I can relax this quality of quasi-geodesic that I obtain to something slightly worse. So I add a 10 to these additive parameters. By the local to global principle, there exists a scale L, so that every L local quasi-geodesic of this slightly worse quality is a global quasi-geodesic. But now, if a representation rho is near enough to the inclusion, then words of length at most L over 2 in gamma satisfy that comparing the distance between gamma p and rho gamma p is at most 10. So that's just one way of saying that you can quantify the nearness of representations by making sure that they don't move points very much on some finite ball in the space. Okay, since gamma acts by isometries, this condition that holds on a ball at the identity of radius L over 2 holds at every ball of radius L over 2 in the orbit. So this orbit map sends geodesics to L local quasi-geodesics, right? This quasi-geodesic condition holds at every L over 2 ball, so for all intervals of length L. And then I'm just applying the local to global principle to see that these local quasi-geodesics are global quasi-geodesics. Now I've shown that the orbit map sends geodesics to quasi-geodesics, so I'm done. This group is, this nearby representation is still results in an undistorted subgroup. Okay. So for the rest of part 1 of this talk, I just want to point out some features about how this works in hyperbolic space and what you have to consider when you want to move on to higher rank. So probably the most important sort of technical lemma that sits underneath all of this is called the Morse lemma. There's another famous Morse lemma that you use for Morse functions. This is named after the same person, but it's a different thing. So the Morse lemma says that for all quasi-geodesic parameters, C1, C2, C3, C4, there exists a constant d such that if a sequence xn is a quasi-geodesic of this quality, hyperbolic space, then for all n less than m, you can find a pair of points so that the first point of this sequence, xn, is within d of p, and the last point of this sequence, xm, is within d of q, and also every intermediate point of this sequence is within d of this geodesic segment running p and q. Okay, so that's the Morse lemma. The Morse lemma implies the local to global principle, and the local to global principle implies that the undistorted subgroups are stable. It's a crucial lemma in the geometry of hyperbolic space, in the geometry of hyperbolic groups. It's definitely something worth knowing. Unfortunately, it totally fails in the context of higher rank. And even though that tool fails, like in addition to the fact that the tool fails, also all these consequences of it fail in higher rank. So I've drawn some suggested pictures that I won't explain now, but undistorted subgroups are no longer stable in higher rank. So you can have a group that's undistorted and nearby representations that are not undistorted. The local to global principle fails. You can have a local quasi-geodesic that's not a global quasi-geodesic. And the Morse lemma fails. You can have a a sequence or array that leaves every bounded neighborhood of every line in a higher rank symmetric space. Okay, so if you want, you can pause the video and think a little bit about what these pictures are trying to say. I'll explain them in part 2. Yeah, maybe I'll say a little bit about what's coming and what we've done. So far what we've done is we've talked about undistorted subgroups and negative curvature. We talked about how classical Techtmiller theory is a special case of that story. How you can see discreteness and stability as a consequence of undistortion. And we talked about the Morse lemma and the local to global principle. Something that I've completely left out, which is interesting, is that the undistorted condition in this context is equivalent to being convex co-compact. Let me not say anything else about it, but that's something interesting you can look into. And then in part 2, what will we talk about? We'll talk about the Anosov subgroups in the higher rank. We'll talk about why being in a higher rank symmetric space makes this more difficult, what you can do to fix it. So there's a definition of something called Morse quasi-geodesics, due to Kapovich, Lieben-Partey, who proved a local to global principle for these quasi-geodesics, which lets you reprove that Anosov subgroups are stable. They gave a definition for Anosov subgroups that uses the language of Morse quasi-geodesics. And then we'll talk about a quantified version of that local to global principle and what that lets you do. Okay, so thank you for listening to part 1. Feel free to come back for part 2.